Thank you. Good afternoon, everyone. My name is Mohammed Haris. I've started my second year in PhD here, and I'm a student in Brunel University, London. I'll be presenting my research on developing coating for improved corrosion performance of fasteners for dissimilar materials joining application. So today, the agenda of my presentation is introduction, literature review, and research motivation, its objective, scope of study, methodology, and future work. So the lightweight material is being studied a lot nowadays. It's a key component in automotive and aerospace structure because it offers some goals related to lower the CO2 emissions. And this is the key trend that drives the automotive and aerospace industries nowadays to make sure the structures are lightweight. So the industries nowadays are doing a lot of research in developing structural components by using different structural materials like multi-material construction. And for that part, they are using different joining technologies, different things. And we know that to join materials, there are different joining techniques like mechanical fastening, rivets, adhesion bonding, or let's say welding, the most important one like we are doing. So for joining, when we join these materials, they are joined by welding, self-piercing rivets, or adhesion. And in these are the driving force behind this one. And in many industrial sector, the multi-material construction are the driving force because of its advantage such as lightweight, strength to weight ratio, and the performance that it gives when it's coupled with other materials. And this enables us to reduce the CO2 emission, which is one part, and the other components. And recent days, the multi-material joints such as CFRP, carbon fiber reinforced polymer to metal, as well as aluminum to steel joint has seen dramatic growth in both R&D activity as well as in commercial application. So I'll be discussing with this. So when these multi-materials are joined together, they tend to possess some electrode potential in them, which is called galvanic series of some of metals, and in which the CFRP sits, graphite and CFRP sits at the most noble part of the chart. As you can see, sorry, low carbon steel and aluminum alloy sit somewhere on the opposite end of the chart, galvanic series. So it poses a question that it gives us a galvanic coupling or galvanic corrosion. So what is galvanic corrosion? Sorry about that. And what is galvanic corrosion? Galvanic corrosion is a corrosion that occurs when two metals are in contact with each other under electrolytic condition. And it usually one metal goes into more noble state as the other metal goes into more corrosive state. The noble state is called cathodic and the corrosion one is anodic. So the anodic part goes severe corrosion as compared to in original state when it's remained uncoupled. So when these materials are joined together for us in a structural component like aerospace or automotive application, the graphite in CFRP, it behaves electrochemically as a noble material, as can be seen from the from this graphite galvanic series. So this one, this poses a challenging things for us because it's a very good electrical conductor having oxide, graphite in oxide form, and it's a very inert material. The ability of graphite to act noble material in whenever it's coupled to any metal in this series, it presents as a challenge that it will result in galvanic coupling or galvanic corrosion. So when this CFRP and aluminum, CFRP is joined with aluminum or any other metal, it results in galvanic corrosion. And these joining are occurred by one of the process that's been widely employed is called self-piercing riveting techniques. So self-piercing riveting techniques is one of the most simplest techniques. It offers us, the reason of choosing this technique is it offers us, it's very uncomplicated technique. It doesn't require any surface finish. It doesn't require post-treatment, and it doesn't offer any fumes or curing time like another process. So self-piercing rivet is when the two or more sheets of material are formed by forming a mechanical interlock like this one, the final process, this one. When punch pushes through a semi-tabular rivet like this one, and it pierces to the top sheet in the second one, and it flares out the bottom sheet, and the counteract die act as a formation of the button surface. So that's a spear joint. It's a very fast process. It takes few minutes to make a spear joint. It's widely employed in the automobile industry. So when we are doing this joint, galvanic coupling is occurring. Galvanic couple tend to form here, and to protect this, a few coatings has been already used in rivets. So these coatings are zinc-based coatings, zinc, aluminum, magnesium-based coatings, and they are widely used as a sacrificial layer on the steel surface until now. So when zinc is combined with other elements like aluminum, tin, nickel, iron, etc., to enhance the corrosion resistance of rivet, they are mostly used for the similar or metallic dissimilar materials. So right now, the commercially available, widely used and widely accepted coating is this one, zinc, aluminum, tin, which is known as Almac coated rivets, and zinc tin coating. That are most widely used rivets in these multi-material construction for joining of aluminum sheets of different thickness, as well as aluminum and sometimes steels. And the other one is zinc nickel coating that is used for steel rivets, but not that much. So how these coatings are being formed? They are widely produced in industry by using mechanical plating method, where we put the rivets in overhead, we put the rivets under this barrel. It's rotating with certain RPM, and our overhead feeder produce the coating material that is being poured into the barrel. It can be automated as well as manual. Automatic feed system can be here that will feed the rivets in this. And the plating barrel is contained with glass bead that hits the surface of the rivet and deposit by using mechanical forces on the rivet surface. The coating thickness that we develop from this mechanical plating of rivets is usually 8 to 12 micrometer. And the rivets are processed through this belt and separated through magnetic separator and dried for further process. So this process has certain advantage. It's very fast moving process. So it produces in one batch, it produces at least 10,000 of rivets. Can produce corrosion resistance coating, and it has excellent adhesion and uniformity for this process. And it offers us the freedom of hydrogen embrittlement because it doesn't involve any high temperature and any analytical process control. So it can easily plate center metal parts, especially, and thicker coatings can be applied with varying parameters without significant cost increase. So what coating methods will I be interested in along with that one? So there are different coating methods that are being used here. CVD is one of them, which will be studied and used to deposit carbon-based coating like DLC, diamond-like carbon coating on the rivet surface. It will be on the surface as well as on the top surface. And then some electrodeposition techniques to deposit coating for aluminum, and then processing it through the second step. Then there are some spray coatings that will be used to study this similar pattern, and it will be done to study the galvanic corrosion between the SPR joint that we've seen in the slide 4. So coming up to the point that why do we need this? Why the question comes up, why we are doing this. So dissimilar materials have been used for industry for a couple of for at least some times. Dissimilar materials are not weldable easily, except for some, but especially aluminum and CFRP are not weldable. They are mostly joined together by adhesive bonding or SPR. So adhesive bonding has certain limitation of curing time and other stuff. That's why we are going for fast processing route like SPR techniques. And this dissimilar material combination has high susceptibility to corrosion as it forms galvanic coupling between the material that's been joining them, like CFRP, carbon steel, and base plate of aluminum or other metal. So despite the widespread use of fastener in automobile industry as well as in aerospace industry, there is a very little or no research being done on the development of faster coatings for CFRP and aluminum and carbon steel galvanic couple to mitigate corrosion. So this study is being done to develop some understanding to mitigate or at least understand the corrosion between the CFRP carbon steel rivet as well as aluminum. So the research objectives of my research are to investigate the galvanic coupling behavior between the dissimilar material by using electrochemical techniques. Electrochemical techniques means I'll be doing potentiodynamic polarization, little bit of electroimpedance spectroscopy to see the coating performance. And the second one will be experimentally determine the corrosion performance of suitable commercial available carbon steel rivets and fastener joint application. That will be the standard available, commercially available coatings, and to determine the mechanical performance of uncoated and coated rivet joints by using single lab shear test. So this one is the uncoated one and coated one. Coated one includes the commercially available as well as the one that I'm going to coat with different coating techniques and different coating materials. So the scope of the study is CFRPs and aluminum will be used throughout my study as a joining material. Carbon steel rivet will be used throughout this study, including doing corrosion and mechanical test. Self-piercing rivet will be used as a joining technology, and all the joints that are being made by using this self-piercing technique. And the study will not investigate the self-piercing riveting parameters such as force type, die force, and etc. So this is already set to industry specified or industry acceptable standard that are made on similar patterns on the coating use here. All the electrochemical tests will be conducted by using 3-cell glass electrode setup, while salt spray tests will be conducted for environmental assessments. Coming to how I'm going to proceed. So as I said that very little is known about the factors influencing the various material condition governing the corrosion of between the galvanic corrosion between CFRP and carbon steel and aluminum. So I'm going to use the standard tests such as atmospheric exposure accelerated salt spray test, electrochemical evaluation of materials like CFRP, aluminum, and carbon steel to generate data, to generate how these things behave in corrosive environment, which will be seawater or 3.58% NaCl. Electrochemical characterization of coating performance that will be done by using different characterization techniques such as XRD, XRF, SEM. This is the flow chart that I'm going to follow, workflow chart. And this is the standard 3-cell glass electrode system. And this is the setup that I'm using to conduct a test for 3 glass cell electrode. And this is my sample for after joint is made, and I'm using the Avesta cell. So this all metal joints will be evaluated in environments such as brine and carbonic acid. These are the solution that will represent the real condition environment that's been observed in automotive sector. And at least 3 samples per test will be performed to get accurate statistical data. So for the single lab shear test, I'll be using this ISO standard 12996 to 2013 that will be followed throughout for the single lab shear test. This is a typical single lab shear test. Sorry. This is a typical single lab shear test specimen. This is the rivet that's being punched through the top CFRP sheet onto the bottom aluminum sheet. The specimen will be pulled from this side as well as on this side. And it will be the mechanical force, the mechanical strength of the mechanical force will be measured by using this single lab shear test, the tensile test. Sorry. So this is the result for the corrosion test that I done recently. This is the basic corrosion test. It's a preliminary results for the Alma coated SPR joint that I did. It's the one that is made of aluminum, tin, and zinc, and it gives us a generalized information of current densities and corrosion potential and general trend. And this will be the comparative data that I'll be comparing with the coated one. So in this one, current density that I obtained was around 35.8 4 by using the anodic and cathodic slope. It's not mentioned here, but it's usually, I did it from the software, and the corrosion potential was around 1.3 millivolt, and that was for this one. Sorry. So this is the base. This is kind of industrially available data that I have, and I'm going to use this one to find how the coatings has been evaluated when the same coating is done for when the different coatings is done for the similar conditions. So I'll be using the mixed potential theory and other techniques to get the performance of the coating. Moving on to the future works, what I'm going to plan. So as I'm a second year, so I plan to do this study, all the deposition of the coatings in this year, and I'm going to have this coating deposited on the rivets while they are used in dissimilar material joints. In my case, CFRP and aluminum. And this coating will be applied using available techniques that I just discussed, like CVD, electrodeposition, or spraying techniques. And then it's going to be investigated electrochemically. Then the mechanical test, I'm going to do that as well for joint strength, which will be done through ISO 12996:2013. And it's going to be done for all the coatings under similar conditions so that it may be comparable. And thank you so much. I would like to thank you, the NSIRC and TWI Brunel University, by which this research has been made possible. And this research for sure has been done in National Structural Integrity Research Center. It's been in TWI for 10 years. We just know. Thank you so much.
Okay, so has anybody got any questions?
Thank you for the presentation. I would like to ask you a question about your polarization curve. So if you would go back to your polarization curve. So you said that you calculated the corrosion rate, right?
Corrosion potential and current density and current potential. Sorry, corrosion potential.
So my question is, when you do the cathode extrapolation, you have to have a linear region on your both of your cathodic and part of the graph. Yeah. So how did you find the linear part? I used the fitting for origin lab, and I just use it at this part, which was more into like cycle. I did this one, it's a combination. I did first cathodic sweep and then anodic sweep separately. So from the cathodic sweep, I got the fitting of that one, and from the anodic sweep, I got the value of that one. But you are right that for that one, it's a linear region, it should be required. But that's why I did it individually and then combined that in one sweep. Yeah, I'm not entirely sure if this methodology is right for this kind of
okay.
Graphs. Thank you.
You're welcome.
Anybody else got any questions? After lunch session. So, from my perspective, a couple of things. For your salt spray test, how long are you planning on running those for?
So there are a lot for the ISO. I'm in like discussion with my supervisor, because there are certain automotive companies that they have their own salt spray test that they run for some 36 weeks.
Yeah.
Some runs for like 45 weeks. So, but we are in a discussion that most probably we're going to go for 36 weeks.
Okay. Yeah.
Yeah.
So the next question following on from that, are you planning on doing any magnographic examination of those joints to see whether there is degradation of the rivets and what's happening in terms of the any corrosion products that may have formed at those interfaces?
So I'm doing metallographic examination in terms of having to see like the cross section of the specimen is, I'm doing that, but not for the corrosion product right now. I'm doing it to check whether the joint has been made perfectly but the corrosion product will, I'm going to surely be doing the cross section as well, because that's where I mentioned that the SEM analysis as well as EDX or XRD will be done through the cross sectioning of the sample. Yeah.
Okay. This is kind of, I appreciate there's lots of standard testing out there, but for some of these applications, in automotive, things are subjected to wet and then dry environments as a cycling test in perhaps
in
not
salt
necessarily
spray.
the same types of joints, but in aerospace you would have fasteners running through composites. Have you thought about any testing that would allow you to evaluate those mechanisms?
So for the aerospace, I'm more inclined towards right now for my research towards the automotive sector.
But in terms of
future
thinking about recycling of what's happening in real life, rather than just a long extended test in a controlled environment.
For aerospace application. You mean for aerospace application?
Not as for any application.
Oh yeah, I can look into that. Yeah. Thank you for that. I'll look into that.
Okay. Anybody got anything else? Okay. So, thank you very much.
Thank you.
Well done. And applause everybody.